Hardent is delighted to announce our on-demand training course, An Introduction to UVM, the Universal Verification Methodology. Starting with the basics of library structure and proceeding through advanced concepts like sequences, analysis, and configuration objects, the course typically takes 12 to 14 hours to complete, including labs. The materials are developed and taught by verification experts with years of practical UVM verification experience. Because the course is delivered online on demand, a student is free to absorb the material at their own pace and on their own schedule. Practical code examples are provided throughout, and detailed lab exercises accompany every major topic. A prerequisite for this course is experience writing object-oriented System Verilog. So if necessary, our on-demand System Verilog for Verification training course leads perfectly into this one. Through 29 video topics, the course presents the student with everything they need to start developing practical UVM test benches. Each topic clearly describes some aspect of modern UVM-based verification, and later topics build on earlier ones to bring it all into focus. Here's a sample of what you can expect. The data to be transferred is usually encapsulated in a class object and referred to as a transaction item. Some communication involves a single transaction, and some imply a whole series. Now, how is this implemented by UVM? Well, all task-based phases maintain a central objection count, the number of components which still have work to complete within that phase. One by one, hopefully, the objections will be dropped as each component completes its work. When the objection count for a phase has reached 0, the phase is terminated. To achieve this, we need to rethink our stimulus generator class. The most obvious change will be to remove the algorithm, the recipe for stimulus generation. Some portion of the stimulus generator will remain in the environment. Let's call this the stimulus controller for now. It handles communication with the driver, including the buffering FIFO, as I'm showing here. These algorithms share the controller and can stream their transaction items in turn to the driver and the finish item blocks the sequence once again until the driver receives the request. The sequence item doesn't stay in the buffer any length of time. It passes immediately to the driver, whose get call has blocked for 0 time effectively. The completion of the get method indicates that the transfer from sequence to driver has completed, which unblocks the finish item task in the sequence. To minimize monitor complexity, UVM supports a broadcast mechanism where the monitor issues the message once, but the message is received by as many observers as are present. Adding a 4th observer to this example would be invisible to the monitor and would scale. Notice that the monitor declares a UVM analysis port called monAP and constructs it in the build phase. Further down in the run phase, the monitor prepares a wishbone transaction item called TXN, and when ready, broadcasts the transaction item by calling monAP.write. The goal of this lab is to reinforce what we've learned about hierarchy by modifying the test bench with an encapsulation class router agent, which gets to instantiate 2 other encapsulating classes, mons and drives, that I've already created for you. So there you have it, a practical, no-nonsense introduction to using the Universal Verification Methodology. For more information about this course and the wide variety of other training and services available from Hardent, please visit our website at hardent.com or email us info@hardent.com.